This video is about area and perimeter. It's found in your text in section 11-1. Okay, let's review what you may have learned in past math classes about area. And we'll start out with the most basic thing of all, which is a postulate that the area of a square, take for example this little square right here, if it has a side of length s, then the area of this square is s squared. So s could stand for anything. As long as we know that the side length is s, the area of that particular square is s squared. And that's a postulate because we accept it without proof. Now, believe it or not, there's a theorem that can be proved that says the area of a rectangle is its base times its height. You can look at the proof of this theorem on page 424 of your book. It may seem self-evident, but actually there is a somewhat sophisticated way of proving it from this postulate that a square has area s squared. Okay, so what we're doing is we're calling this little box one square unit. It doesn't matter at this point what the units are. As long as we are counting squares, we can define area as the number of squares, square units, that is, it takes to cover up a two-dimensional shape. So the area of this rectangle then would be the number of squares it takes to cover up this rectangle. So let's count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So the rectangle has an area of 12 square units. Or sometimes we write 12 units squared like that. That's the area of this rectangle, the colored rectangle here. And we did that by counting the squares inside of it. But if we count along the base of the rectangle, we have we're going 3 steps along the bottom plus, times the height, which is 1, 2, 3, 4 steps. We have 12 as well. And so intuitively you can see that this theorem is true. Okay, let's review the idea of perimeter. Perimeter is the distance around the edges of a two-dimensional shape. So if I were to take a walk around this, suppose that this were a flower bed, and I wanted to walk around the edges, I would have to walk a distance that would be equal to the perimeter. So let's just count. I would have to take 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 steps, as long as each step had a unit length. So the formula for perimeter actually makes sense because what we're doing is we're counting the steps on the base 2 times, right? We're counting 3 steps for this leg of the journey and 3 more for this leg of the journey. We're also counting the number of steps along the height 2 times. So we have basically 2 times the base length plus 2 times the height is the perimeter. And that's where we get this formula. What we've done here is just factored out a 2, and you have the perimeter is 2 times the quantity, base plus height. Let's see if this works. 14 steps, we counted around. Let's do this using the formula. 2 times the base measures 3 units. The height measures 4 units. So we have 2 times 7, which gives us 14. Sure enough, and that's going to be 14 units, not square units, it's just plain units. because the unit in this case is a measure of length. Square units would be a measure of area. Let's do an example problem where we're asked to fill in the missing values in this table, which refers to the dimensions of a rectangle. So I'm going to draw a diagram of our rectangle. We're told that the base measures k plus 7, and we need to find what the height is going to be. So I'm just going to label that h. Well, it doesn't look like we have very much information here. We're given that the perimeter is 4k plus 20. So we must have to use the perimeter somehow in this problem. So the formula for perimeter is 2 times the quantity base plus height. So I'm just going to play around with this by plugging in what I know about the base and the height. I have 2 times k plus 7 plus the height. Okay, and I'm given an expression for what that perimeter equals. So I'm going to put that that equals 4k plus 20. Let's keep in view that we're trying to solve for the height here. So I'm going to try to get the height by itself on one side and everything else on the other side of this equation. Dividing both sides of this by 2, I have k plus 7 plus h equals, I can divide each of these terms by 2, 2k plus 10. And I'm still solving for h, can't lose sight of that. I'm going to subtract k from both sides and 7 from both sides. So I'm going to be left with h equals, only 1k is left on this side, 10 minus 7 is 3. So I have h equals k plus 3. That doesn't look like much of an answer, but I am allowed to leave things in terms of k in this table because they've given me the values in terms of k. So h I'm going to fill in is k plus 3. Now I need to find the area, and I know that the area must be base times height. All right, well, I can fill in something because I have things here for the base and the height. So the base is k plus 7, and the height is k plus 3. Then I can FOIL this out, so I'm going to have k squared plus 7k plus 3k plus 21. I can combine these two middle terms because they're like terms. So I have k squared plus 10k plus 21 is equal to the area. And that's as far as I can go because I don't have a value for k. In this problem, I'm leaving everything in terms of k. So that is the answer that goes in that spot. You try one like this. Fill in the missing values in this table, which also refers to the dimensions of a rectangle. Okay, now we come to a postulate that might be somewhat new, even though you'll probably have a sense for it intuitively. It's the area addition postulate, which says that the area of a region, even a funny-shaped region like this or like this, is the sum of the areas of its non-overlapping parts. So in other words, if we can cut up a shape into different mini shapes and then add up the areas, say, of region 1 and region 2, we should get the area of the entire shape. Okay, in this case, region 1 and region 2 are easy areas to find because they're both rectangles. Region 1 has a base of 2 and a height of 6. Region 2 has a base of 1 and a height of 2. So the area of 1 plus the area of 2 would be 2 times 6 is 12 plus 1 times 2 is 2, and that's 14 units squared. And sure enough, if you count up those squares, you'll count up 14 squares. So that checks out. Now, with a shape like an irregularly shaped shape, like the one down here, it'll take some more sophistication than we have at this point to find the area of the entire thing because we don't have an area formula yet for parallelograms. But the same basic idea holds, that the area of region 1 plus the area of region 2 adds up to the area of the entire shape. Okay, let's do an example using this postulate. We're asked to find the area of this figure, assuming all consecutive sides are perpendicular. So let's divide this up into two regions like we did just a moment ago. We have this bigger rectangle and this smaller rectangle, and we're given dimensions of both of those. So the bigger rectangle is, so I'm going to write 1 plus 2 is my total area. The area of region 1 is 3 times 8 plus area of region 2 is 2 times 3. Okay, so I have 24 plus 6 is the area, so that 30 is the area of that shape. So think for a second. Could you find this big L-shaped area in some other way that would also use the same principle but not be exactly the same method? What if you imagined this big shape and then you subtracted this sort of ghost area? You could actually make something like an area subtraction postulate if you called this big shape, let's say region 3, so that region 3 minus, if you called this region 4 would also be the area of the blue shaded shape. So the area addition postulate also works as an area subtraction postulate, simply because region 4 plus the region we're looking for gives us the larger region, which I've labeled 3. You try this one. Find the area of this figure, assuming all consecutive sides are perpendicular. Okay, another example here is going to tie together some ideas that we've had recently. We're asked to find the area of this figure, assuming all consecutive sides are perpendicular, meaning this is a rectangle, so that shouldn't be too difficult, except they are not giving us the base or the height of this rectangle. All they're telling us is the measure of the diagonal, and they're giving us that this angle measures 30 degrees. So fortunately, we recognize special triangles now. We know that this must be a 30, 60, 90 special triangle here. So since we know the hypotenuse of that special triangle, we can easily find the two legs. So for a 30, 60, 90, the shorter leg is going to be half of the hypotenuse. So we have that this is half of 18, which is 9. The longer leg is going to be the square root of 3 times the measure of the shorter leg, which is 9. So this is 9 times the square root of 3. Okay, now we've got the base and the height of this rectangle. So base times height is simply going to be 9 times the square root of 3 times 9. And we can multiply these 9s and we get 81 times the square root of 3. For further practice with this, see page 426 of your book, numbers 9 to 13 odd and numbers 17 to 31 odd.